All right, so this one, it's also not taken out of our book. So you'll have to bear with me on the figure here. Okay, so here the blue lines represent a pipe. Okay, so this is a pipe that has two segments, and then there would be like one of those little elbow pieces here, 90-degree elbow pieces. So one end of the pipe plugs into that elbow, the other end plugs in, and now you've got a pipe that makes a 90-degree angle. Okay, if you ever tear your walls apart and look at your plumbing, you're going to see this kind of thing. One length of pipe right along the y-axis, 8 inches long. Then you've got your 90-degree bend. The other piece of pipe, 6 inches long, and it's angled 30 degrees below the XY plane. Now notice the XYZ axis is a little bit different than what we might be used to working with. Like I said, you might see the XYZ labeled different ways, so just pay attention to which axis is X, Y, and Z. Don't just assume that it's always going to be X, Y, Z. It could be other ways. As long as we obey the right-hand rule, it's a valid coordinate system. So if I take my right hand, fingers along the x-axis, curl it towards the y, z goes up. It's a valid coordinate system. So anyways, we're asked, what is the moment of the force couple? So what you see is that there's two forces that are vertical. One is vertical up, 25 pounds, the other is vertical down. Equal magnitude, parallel lines of action, opposite sense. It's a force couple. We want to know what is the moment of that force couple. And as we saw before, we can work this out using our cross product, position of A with respect to B, cross the force at A, for example. And whatever that result is, it would be true if we were to take the moments of these forces around any point. So let's see what happens here. Now, I meant to point this out when we had the two cross products worked out from the previous example, but if you check, one of them had a lot of minus signs in it, the other one had a lot of positive numbers in it. Because you get the same result either way, if you can see in advance that one's going to give you a lot of negative numbers and the other's going to give you a lot of positive numbers, you might want to just go with the positive number way of working it out so that you don't open the door for missing a minus sign and throwing your whole problem off that way. Now in this one, I don't know, if I write the position of B with respect to A, I'm going to have some positive and negative components. If I go A with respect to, I get it seems like I get a mix either way. Okay, so I don't know if it really matters which way I write this, so let me just go with what we had before, which is that the moment of this force couple, position of A with respect to B, cross the force at A. Like I said, if I could see that, I would get a lot of negative signs writing this way. Then I might want to try the position of B with respect to A cross the force at B. But just at my initial glance, I think we're going to get a pretty even mixture of positive and negative numbers, so I don't think it really matters here. All right, so let's see here. We have I, J, and K across the top row. It's just a plain old simple cross product. So I, J, K go across the top. It's only when we have the mixed triple product where there's a lambda dot, the result of this, that we put lambda components up here. Remember, cross product is going to give us a vector result, so we better have some I, J, K vectors to get our vector result at the end. Now the position vector, let's skip that one for a moment. Let's just do the force vector because that one's probably the easier of the two. The force that's being applied at A, well, it's pointing straight down, so that means it has no x and y components since the z axis is the vertical one. So I'm going to have a 0 and a 0, and then the 25 pounds is in the negative z direction, so I'm going to put a minus 25 here. Now my position vector, the position of A with respect to B, that means I'm starting at the point B and I'm trying to get back up to the point A. Well, notice what I have to do if I want to get from the point B to the point A. I'm going to have to make some movement up in the positive z direction and then some movement to the right in the negative x direction. Okay. So what I need is I need to know, okay, well, how far am I going up in the z and how far am I going to the right in the negative x direction? Well, because there's 90 degrees between the x and the z axes, what I've got here is a right triangle. Okay, a line that goes, I probably should have drew it a little bit more vertical than I did, but it's going straight up and then straight back, so it's 90 degrees there. And so if I need to know this distance, I might take 6 times the sine of 30, since 6 represents the hypotenuse here. And for the leg of the triangle, that would be on top here, representing our distance in the x direction. I might say 6 cosine of 30. Okay, so if you got the actual values, fine. I'm just going to leave it like that for now. Now, as far as putting this into the 3 by 3, in the x direction, I'm going to the right. That's negative x direction. So I'm going to put negative 6 cosine of 30 here. Okay, you might have the number if you actually multiply that. We said that there is nothing for the y, because the only movements we're making are in the z and in the x directions. We're not moving left or right along the y-axis here. So I'm going to have a 0 for j. And then we have, in the z direction, it was a positive movement going up. So positive 6 sine of 30. Okay, and I believe that would be 3 if we multiply it out. All right, but regardless of whether you leave it unsimplified at this point or not, we can multiply this 3 by 3 and see what happens. If I cover up the I column, 0 minus 0, so I get 0i. Minus, when I cover up j, let's see, something happens here. So I'm going to have minus negative 6 cosine of 30. Times negative 25 minus 0 plus, when it comes time for k, I get a 0 minus 0, so I get a 0k. Okay, so all you got to do is multiply that out. Let's see, we got negative times negative times negative, so it's going to be a negative result. And 6 times 25 is 150. 150 times the cosine of 30.
75 root 3.
75 square root of 3. Okay, because cosine of 30 is square root of 3 over 2. So our 150 divided by 2 is 75. 75 times square root of 3. and that's in the, don't forget the minus sign that was in the front here, so minus 75 squared root of 3. J, what do we got here? Also inches, is inches per pound. Or pounds, inches. If you got it as a decimal, if you actually multiply that out, what do you get? You get something like negative 130. How about you check it? Negative 130.
Yeah.
J. And I think for, even though you could say inches times pounds and pound times inches, I think sort of the standard is to put the force first. Doesn't really seem to matter much, but we'll call it pounds times inches. Stick with what most other people tend to do. Okay, so 3 dimensions, things kind of work out the same way. That one wasn't bad because so many zeros showed up in the 3 by 3, and that's always a nice thing when it happens. But nevertheless, you just need to ask yourself, how do I get from the point B to the point A? That's your position vector. And then it was nice here because the force vector was strictly in the z direction. Yeah, question?
So the origin axis is the y-axis?
So this force couple wants to create rotation around an axis that would be in the y direction, okay? Not necessarily the y-axis itself, but an axis that would be parallel to the y-axis. Because remember, this represents the moment of the force couple about any point. So if I were to take the point A and say, okay, I'm going to hold that point fixed, that's the only point I'm going to hold fixed, and I'm going to apply this force couple, I would get rotation around the y-axis because the point A is on the y-axis. If I were to take the origin and hold that point fixed, I would get rotation around the y-axis because the origin is on the y-axis. But if I were to take this point over here and say, let me take the moment about this point, I would get rotation. Now that point's not even on the rigid body, but let's say that somehow we could hold that point fixed. Maybe the pipe extended out this way as well, and we held this end of it fixed. We would get rotation around an axis that sticks out of that point and is parallel to the y-axis. Okay? So if we had another segment that came here and I held that point fixed, I would just get rotation around an axis parallel to y, but coming out of a point that we're holding fixed.
And the rotation would be clockwise in that axis?
The rotation would be clockwise if we were sitting out at the positive end of the y-axis. So if we were out this way and we were looking back, we would see clockwise rotation. And usually the direction of the rotation is, for the most part, pretty easy to see just from the orientation of the force couple. Okay? You can see that this is going to want to create clockwise rotation just because of this one being down and this one being up. Okay, so the directions here usually aren't too difficult to discern.